To a large extent, the types of problems that we have been doing so far are fairly unrealistic. When a truck rams into a car, they're not going to continue moving along one line. One is going to veer a little bit to the left and one is going to veer a little bit to the right, and we're going to have a two-dimensional motion problem. So in this video, we will talk about how to use momentum to explain these sorts of situations, how to organize a solution. The notes in your homework, in the practice work, really outline the exact same thing I'm going to show here. I'm just going to talk through it. So this is just if you need some help understanding what those symbols and so forth mean. So in our question here, a car is going to be colliding with a truck, and they will not be moving along the same line, along a single line. You can see here that the car moves to the north and the truck moves not quite south, but a little bit south of east, so sort of in this sort of a direction. Okay, so that kind of gives you a sense of what the collision looks like, but of course that's not a very useful way of drawing our arrows. We'll come back to that picture in just a few minutes. When we're working with momentum, we want to make sure that we're not just drawing our vector diagrams with velocities like we've maybe done in the past. I want to first figure out the magnitude of the momentum for each of my objects, and then put those together in a vector diagram and follow my rules for vectors that way. So the car originally has 12,000 kilogram meters per second squared of momentum, again to the north, whatever direction was given in the problem for the speed or the velocity, that's going to match the direction of the momentum as well. And then the truck, I'm going to be thinking about that not as 10 meters per second, but as 10,000 units of momentum. And then after the crash, the car is still moving, but now it's moving at something of an angle. Okay, so that's a good first step, is to figure out those values of momentum rather than just be thinking about velocities. And then the diagram can really help you visualize what's going on. This is certainly optional, but it definitely will help you see what's happening. Again, this first sketch here is similar to what I just quickly drew at the beginning, but that doesn't really help us mathematically. The way we want to think about things combining, looking at what is the total momentum before the crash, we want to be putting these vectors together head to tail. So our truck is traveling to the north, so that's our arrow just straight up in my picture, and then that was the car is traveling to the north, and then the truck is moving at 20 degrees south of east. So I start from the end of that head and begin the tail, and so we end up with this sort of picture. Now, this dotted arrow that I have here, that is not any single object's momentum. That's the total momentum of the system, and that would have to equal that momentum afterwards of the car, the 3,000 kilogram meters per second. That's 10 degrees north of east plus something, and that something is what we're going to try to figure out so that we can find the velocity of the truck. You certainly don't have to put your solution in such a formal way as I have done, but using unit vectors is a nice way of keeping things organized. So what I've done here is I've taken the amounts of momentum that I calculated and used sines and cosines to find the I hat and j hat, the components of the vehicles. And for the 20 meters per second north, which made it 12,000 kilogram meters per second north, that's just a j hat. And then this 20 degrees south of east that we had for the truck, you could put in negative 20 for your angle as a standard angle, or you can just be thinking that it's going to have a positive x component and a negative y component. So either way, but you have to take into account that direction, just like you would if the truck was moving to the left, how you would put in a negative value of v for our earlier problems with momentum. So there's a before and an after. The after is known for the car. Okay, so similar sorts of things here. The 10 degrees north of east would produce two positive components. And then I don't know the momentum of the truck. So I'm just going to call those that momentum rather than leave it as just, well, what's the momentum vector? I'm going to break it into two components, one in the x and one in the y direction. Because what I'm going to do with all of these values here is I'm going to set up two different equations. I'm going to set up one equation with these numbers here in the x direction, and then I'm going to set up a separate equation with the y direction. And so when I'm working with two-dimensional momentum problems, you want to be doing two problems sort of simultaneously. Break everything up into the x and y parts, work a problem in each direction, and then in the end we're going to put this all back together again. So that's again the final step here. We have the total momentum in the x direction equal to the total momentum in the x direction before and after the collision, and we end up with the momentum of the truck afterwards. Divide that by the 1,000 kilogram mass, and we have our velocity. So we have a similar thing then in the y direction. So we have these two components. The truck is moving north of east. I can tell that because these are both positive values. It's a little bit more in the north direction than the south direction, but I would just set up a triangle and put my components in. The 6.4 would be here, and the 8.58 would be here, and that's where this is coming from. But again, kind of just putting together our vector understanding from earlier in the year and our linear momentum understanding from recently, and just being able to handle this more complex question.